Assalamu alaikum warahmatullahi wabarakatuh. My dear students, I am here to explain and clear the concepts of electrical circuits for any competitive exams so that you can score more and you can get better opportunities in the future. So, without wasting time, let's start. So, here, like our Jahazi exam, national level exam, or Mahar exam, which is called readiness exam to complete your graduation, then formulated all the important topics and important concepts which can be useful because this subject already you studied in level 3 and level 4, maybe have a weak memorization, so you may forget it at this stage of graduation. So I will just recall it and recollect your knowledge so that it is easy for your competitive exams. No need to study the complete syllabus again from step by step. Just you have to recall and summarize with the equations and formulas which has to be memorized and concept should be cleared. So here for Jahizia exam, we call it as knowledge units. This is a specific knowledge unit is electrical circuits. In that, what we have to study so that we can face the exam with to get the better score. So first topic you have to study about the basic elements, circuit elements like resistor, inductors, and capacitors. Then we have to solve problems using Ohm's law, including power representation. So here Ohm's law triangle I will explain, and power equations I will represent. Next, we have to analyze and design simple circuit containing RLC circuit. And this RLC circuit, we have AC and DC concepts here we have to study. First, we'll start with the DC, direct current concept. Then we'll add AC components in it so that it will be easy to recall your subject. Analyze basic electrical circuits using Ohm's law, Kirchhoff's law, Thevenin's theorem, Norton's theorem. So here Ohm's law will comes with the resistance, its parameters, how it is defined. And Kirchhoff's law, we have Kirchhoff's voltage law, which Kirchhoff's current law. And then we have mesh analysis and node analysis also in that. Then we go for the theorems to analyze big circuits to get a single element behavior by using Thevenin's theorem and Norton's theorem. We have many other theorems, but here it is mentioned only two theorems, so we'll study about these two theorems only. Now explain the difference between resistance and reactance, the meaning of phase, and the effect of frequency on capacitance and inductance. So here the AC circuit concept will start. So what is the difference between the resistance and reactance when alternating currents are included? The previous topics all are with the DC concepts only. When alternating current, sinusoidal voltage currents are included, then what is the effect on the resistance, what we call that we will see, and what is the meaning of the phase when the inductance and capacitance are included in the AC circuits. The phase will come into picture, how much it is phase difference, how much it is lagging or leading, it will come. And then the frequency effect on the capacitance and inductance, how its reactance will increase or decrease, how it will behave. Then when frequency becomes 0, then how it will behave like a DC circuit. We will study that one. Now design and analyze simple resistive and RLC circuit using circuit simulator. Here circuit simulator we already studied in the lab, where we just used simulation technique like what we studied in the lab. Some softwares we already used in that. Workbench we used, and we have circuit maker we used. So many some softwares we used. How they will behave by using this RLC circuit we have to analyze. That is, I think, not that much needed because in the competitive exams this cannot be used or this cannot be asked, because simulator we cannot use while answering the questions in the competitive exams or MCQ exams. So remaining all topics I will cover with the important formulas, important concepts then, so that you can just remember those formulas and apply whenever a question is asked. So let's start. So I am Syed Jafar Ali from Computer Engineering Department, College of Computer Science. So let's start our first topic. We have 8 slides here. Then first, Ohm's law, we already know Ohm's law, which is V is equal to I times R, I multiplied by R. That is, I is the current, V is the voltage, and R is the resistance. If you rearrange this, current will be given by V by R. This is already you studied many times from the what we call before graduation also. So resistance is given by, in terms of equation, V by I. So V is equal to IR is Ohm's law, which you remember you can rearrange in the another two forms with the current reference and R reference. So what is R there? It's voltage is proportional to current for a fixed environment, and that proportionality constant is called resistance, and that is called Ohm's law. So what is R actually? R is the resistance, is the material property to oppose the electrons, right? Already we know the resistance. What is resistance? Is the a property of material which oppose the flow of electrons. Now this equation is given by rho L by A. R is equal to resistance in terms of material. If you consider in terms of material, then it is given by rho L by A. So rho is equal to resistivity of material, which is measured in ohm meter, which will vary from copper, aluminum, silver, many materials. Their resistivity will vary, but strong and good material we use as a copper only. So L is the length of the conductor in meters, and A is the cross-sectional area in meter square area. So if you on this resistance, some questions may come, like if what is the effect of the resistance for a material if its length is doubled and area is also doubled, means length is twice and area is double, so the resistance won't change. Now if let us take the area is double and what is the resistance? So area is inversely proportional to resistance, and if it is doubled, then the resistance will be half, because it is inversely proportional. If length is double, then resistance also double. So like this some questions may come. So coming to its structure, if you can see here, the structure is this. If it is the length of the conductor, we can say, then its the cross-sectional area is this one, and this is the length. Then material resistivity will be rho, which varies material to material, like copper, silver, aluminum, steel, like that. So its representation is like this: resistance with voltage V and the direction of current if it is going inside, and its plus minus is the polarity. Now current inside is going to the resistance, means it is always resistance absorbs the energy, or we can say dissipates the energy. Resistance always dissipates, not like a capacitance and inductance that we'll study in that topic. Here resistance always dissipates or absorbs the energy. It's okay. So now the triangle of the Ohm's law, we can say VIR, same equations what we have here. I formed it in the triangular. You put VIR anywhere in the triangle and you can form a equation. V is equal to IR, V on the top, then IR, then R will be V into I is equal to V divided by R. These are divided. Single dot means multiplication. Either two dots means division. Two dots means division. R is equal to V by I. Same I is equal to V by R. Now let us take how the resistances connected in series and what is the equation. If two resistances are connected in series, then its voltages drop. We call drop means absorption. When the current is flown through a resistance, I multiplied by R. Observe, I multiplied by R is called voltage. Already we know that is called voltage drop. Means it is dissipating or absorbing some voltage or power, we can say. So that is nothing but voltage, and V1 is here, and another resistance which is not equal to this R1, then the voltage here will be different. So it is V1 and V2. If R1 and R2 are equal, then V1 also, V2 will also be equal, because in the series circuit the current will be same. In series circuit, single current will flow based upon the summation of these two effective resistance and based upon the source voltage. The drop will be different, the voltage drop, the dissipation will be different. Okay, so here series circuit, the total resistance is always summation of R1 plus R2 plus R3 plus dash dash, it will go R equivalents. Now voltage is given as V1 plus V2 plus V3, like this it will go, because it is the multiplication of the current is nothing but voltage with the resistance. So that's why V1 plus V2 plus V3, and current in total is nothing but, if you want to consider current in resistance R1 as I1, if you want to consider, then in the current in the resistance R2 as a I2, then all currents are equal, because in the series circuit the current will be same. So I total is nothing but R I1 is nothing but equal to I2 is equal to I3, all are same, only voltages will be divided based upon its resistance value. That is V1 plus V2 plus V3. So this is about the series. Now coming to the parallel. If they have a parallel resistance here like this, two are connected like in parallel shape, T shape or pi shape we can say, then the resistance summation will be not like R1 plus R2 plus R3. It will be 1 by R1 by 1 by R1 plus 1 by R2 plus 1 by R3, which is equivalent to 1 by R. That is 1 divided by R is equal to R total. 1 divided by R total is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R3. It will go like that. Later we have to find R by inversing that 1 by R total. Now here in this circuit we can observe here current what is supplied from the source voltage is I. Now the current in R1 is I1 and current in the R2 is I2, means current here is dividing. In the previous case in series voltage is dividing, but in the parallel only current will divide, and the voltage will same here. So supply voltage is here, same will be here in R1, same will be in the R2. So current is division possible in parallel resistance, voltage division possible in the series resistance. So like this, total resistance is given by 1 by R total is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is your equivalence for easy. Now if you want resistance, then make it R1 by R1, what is the value, then that is your R total. Voltage is V1, V2, V3 all are same because these are in parallel, or voltages will be same. Currents now here divide, and that will be given as I total is equal to I1 plus I2 plus I3, and it's based upon the resistance value. So like this series and parallel circuits. Now power, when you come to the power, we have, let us check, this is the block where resistance is there, then power is given by P is equal to plus VI if the current is entering to the block. The block may have resistance, inductance, capacitance, whatever may be. So power is equal to V into I if the current is entering through this positive terminal. Now if the voltage source is voltage is across this block is plus or minus, current is leaving, then power is nothing but minus VI. So always the power when it is entering to the positive terminal and P is equal to plus VI is your equation, it means power absorbed. Now when P is equal to minus VI, that is current leaving from this block, then it is called power delivered, means power is going out. Here power is going in, absorbed. So power is giving to outside, so that is called minus VI. So electrical power in terms of Ohm's law also we can include here. P is equal to VI is a general equation. Now substitute what is V in terms of I and R. What is V in terms of I and R is nothing but V is equal to IR. Substitute here IR in terms of V, that I multiplied by I square, and R will be like this, I square R. Now another equation for V into I, we substitute what is I. So I is nothing but V by R. So substitute here I is equal to V by R. So V into V square by R is your equation. So this is your power. So now coming to the another concept. What are the nodes? What are the branches? What are the loops? We will study now. So what is a branch? Branch represents a single element such as a voltage source or resistor. So here branch, some confusion we have. Branch means only resistance. No, a branch is a point in between two points, we can say, or two nodes. A branch is nothing but a element, we can say. Also branch, element, both are same. Here it may be a resistance, it may be a voltage source, it may be a current source, whatever it may be. A branch it will represent. So we have a voltage source in series with a resistance. So it doesn't mean that these two become one branch. So voltage source is one branch, 5 ohms resistance is another branch. 2 ohms is another branch, 3 ohms is another branch, and current is also another branch. So we have 1, 2, 3, 4, 5 branches here. So this is called branch. Now coming to the node. A node is a point of connection between two or more branches. So here the node is a point of connection between two or more branches. Now here see there is a voltage source and there is a resistance. There is a two branches. So in between this is called node. Means two different branches. Different means here resistance is different. If two resistance are in series, are two different types of branches. Like one is voltage source, one is resistance. So in between the connection is called a node. The connection between two elements is called a node, or a connection between two branches is also called as node. So like this we have 1 and 2 and 3 nodes. Why? Because here in between these 2 ohms and 3 ohms there is no element here, so that's why it become one node. I told you the connection between two elements, one element or two elements is called a node. So there is no element in between this node and this point and this point, so this become together one. And here also there is no element here, so this become one. So all together will form as a one node here. So don't think here 1, 2, 3 nodes are there. No. Now coming to the downside also, between the 10 ohms resistance and 2 ohm resistance, there is no element here. So one node. Between 2 nodes and 3 ohms, there is no element in between. So this is also same node. 3 ohms and 2 ampere, there is no element here or branch here. So this is also same node. So we have common, this is called one node and this is called one node and one here. So A, B, C, 3 nodes we have. 5 branches we have till now. So this is about the branch and node. Now what is a network? A network with B branches, N nodes and L independent loops will satisfy the fundamental theorem of network topology. Now what is loop? Loop is nothing but when you start from one node and it will come back to the same node. It is called, without repeating it. So it is called one loop. Like this, the 10 volts, 5 ohms and 2 ampere, 2 ohms is one loop, we can say. Same thing here, 2 ohms and 3 ohms in one loop. Same thing here, 3 ohms and 2 amperes another loop. So like this we have 1, 2, 3 loops. So like this we can formulate one equation based upon the loop topology and the node topology and branch topology. That is, a network with B branches, N nodes and L independent loops will satisfy the fundamental theorem. B, number of branches is equal to number of loops plus number of nodes minus 1. Now compared to this here. So let's take, we don't know the branches, we know the loops. Let us take, so 1, 2, 3 loops. So 3 plus number of nodes, 1, 2, 3. So 3 nodes. So 3 plus 3, 6. 6 minus 1, how many? 5. So 5 branches are there, not check it. 1, 2, 3, 4, 5. 5 branches are there. So like this it satisfies the equation. We proved that this equation is correct. Now coming to the node, at a particular node, for example A or B or C is there, I am considering like one node at B, let us take, but it's not same, but B, one node. At a particular node, some elements or branches are connected. How many branches are connected here? 5 branches are connected. I am not showing here what is it in these branches, resistance or voltage source, for the easy. But how you identify this branch current together at this node? At this particular node, we can see the direction of these currents and we can form the equation. How? Like I1 is entering to the node and I2 is leaving, I3 is entering, I4 is entering, I5 is entering. So put one side all entering with summation and leaving with summation on other side, like this. I1 is entering, so I put I1 plus I3 is also entering, I put I3, and I4 is also entering plus I4. Remaining 2, I2 and I5 are leaving, so equal to I2 plus I5. So at a particular node, what are the currents entering, summation is equal to what are the currents leaving, its summation is balanced. So there is balance must be 0. So if you take out this I2 plus I5 in this side, it become I1 plus I3 plus I4 minus I2 minus I5 equal to 0. The summation of the currents is equal to 0 at a particular node. In that, it may have addition, it may have negation also as per the direction of the current. So this is your Kirchhoff's current law. So Kirchhoff's laws, we have two: Kirchhoff's current and voltage. So Kirchhoff's current law is nothing but currents entering a particular node is equal to current leaving a particular node and its summation. Like this, if we have a loop, Kirchhoff's voltage law is basically for a particular loop. In this loop, we have a voltage source, we have resistances of R1 and R2, two resistances, and another voltage source and some block. It may be resistance or it may be voltage source, we don't know. Let's see. Now this is the loop. Already I told you, if it starts from one node and it kind of completes a path and return to that node without repeating it, then it is called a loop. So in this loop, the sum of the voltages is equal to 0, maybe some negative, some positive, depends. Or and we can say, if you start with the arrow, current leaving from plus terminal, current leaving from plus terminal, if you take V1, here also current leaving from plus terminal, it is a V4. So V1 plus V4. Current entering a plus terminal is other side we can keep, or we can put as a minus also. So it is on current entering a plus terminal, it is V2, and current entering plus terminal is V3, and current entering a plus terminal is V5. So one side one voltages and other side other voltages based upon the current entering and leaving to that terminal. It may be plus or minus. If it is plus, then one side you can add and keep it aside, and if it is entering, and you can add those voltages and keep on other side. So like this, we have V1 plus V4 equal to V2 plus V3 plus V5. This is one way. Another way is, if the current is leaving from plus terminal, you can take it as a minus V1, and if a current is entering in a plus terminal, you can take it as a plus voltage. So that's also we can say V sources is equal to V drops, is nothing but Kirchhoff's voltage law. Sources, how many sources we have? V1 and V2. How we will identify the current leaving from the sources? Always current leave from the source voltage, or current leaves from the current source. So leaving always. So it is sources we call. Current enters in the components, or we can say resistance or inductance or in capacitance. Current enters in them, where the voltage is taken as drops, means it absorbs the energy. So it is taken as a drop of the voltage that can be kept other side of the equal to, that is V drop 1, that is V2, V drop 2, that is V3, and V drop that is V5. So these are in this side, and V sources V1 plus V4 we can keep. So like this we have some Kirchhoff's current law and Kirchhoff's voltage law. So another definition we can see, the sum of the currents entering a junction equals to the sum of the currents leaving the junction is always known as Kirchhoff's current law. See that wordings is important here. Current entering and current leaving. Sometimes he may say current entering and voltage leaving also. So words are important. Current always flow from one point to other point. So currents entering is equal to sum of currents leaving, is nothing but Kirchhoff's current law. So Kirchhoff's voltage law is nothing but sum of all voltages around the closed loop is equal to 0. So now rearrange this equation, V2 plus V3 plus V5 in other side, it become as V1 plus V4 minus V2 minus V3 minus V5 equal to 0. The sum of voltages around the closed loop, this around the closed loop. Kirchhoff voltage law always dealt with a loop, means it must be a closed circuit. Currents law, Kirchhoff's current law deals with a particular node, how many branches connected and how many currents entering, how many currents leaving. So this is about the branch, node and loop and Kirchhoff's laws. So this is, then go to the another slide. What is the inductance? What is the capacitance? So this is your capacitance. If two plates are placed nearby, and if there is a dielectric between, dielectric maybe air or some material, then it's called a dielectric, which is a non-conducting. Dielectric always a insulator, we can say. Dielectric is always an insulator which is placed in between these two plates. Plates means here we can say electrodes also, we can say positive electrode and negative electrode. Because of this voltage source, this positive charge will be here on this left side electrode or plate, and the negative charge will be on the right side of the plate. So like this, a capacitance will be formed. So capacitance is the ratio of the charge on one plate of the capacitor to the voltage difference between two plates measured in farads. So what is the charge? Q divided by the voltage difference, means what is the voltage we applied, that is nothing but your capacitance. So Q divided by V is your capacitance. Now, based upon its area and its what we call distance in between the plates, or how we categorize the capacitance based upon its structure, we can say C is equal to epsilon R epsilon R and A divided by D. A is the area and D is the distance. So where C is the capacitance, always measured in farads. Generally, it will be microfarads and nanofarads, picofarads. It's very small value. A is the plate area. The plate area. A is the plate area. Now D is the separation between the plates in meters. The distance between these two plates. What is the separation? Generally, very small, milli or milli micrometers only, not much. So generally measured in meters. So it will be in 10 power minus 3 or minus 6, like it will be there. So epsilon 0 is called permittivity of free space, and ER is called relative permittivity, dielectric constant. It's a dielectric constant. What the material we are keeping between these two plates, its permittivity of free space if it is air. Then if we have permittivity of dielectric constant, some material if we are keeping other than air, then it's relative permittivity we have to multiply here. So we know the equation as per the definition. C is equal to charge accumulated on the plate, one of its plate, divided by voltage difference, right? Voltage difference between these two plates. What is the voltage applied or difference between these two plates? Now, what is the total capacitance in series? If two capacitors are connected in series, then it's the opposite to like a resistance. It is 1 by C total is equal to 1 by C1 plus 1 by C2 plus, like this it will be there. Exact opposite to the resistance in series. Means it is same like a resistance connected in parallel, which is equal to capacitance in series. Capacitance are connected in series. Now, what is capacitance in parallel is like a capacitance connected, resistance is connected in series. It is C total is equal to C1 plus C2 plus C3, like this, if they are connected in parallel. So as per its cross-sectional area, because of this equation, and this is called a inductance. Now see the structure here. There is a cross-sectional area, some material is there, it's called core material, on which we rotate the conductor, we can say, and it is maybe copper or silver, may whatever may be the conducting material. This is a conducting material. If you rotate like this, and if you keep connected the voltage source here, then these are called number of turns, means how many times you rotated on this core material, and that turns distance is called length, means starting to the ending, how much is the length of these turns. So then these all are formed for the inductance. For inductance, what is inductance? Inductance is the property whereby an inductor exhibits opposition to the change of current flowing through it, measured in henries. So whenever you apply a voltage source here, some current try to flow in this conductor, but it opposes the, due to these turns, number of turns and length and cross-section area, it try to oppose the change rate of change of current, means movement of the current through this material. Then it is called the inductance, and it is measured in the henries. Equation based upon its structure is L is equal to mu n square A by L. So where A already I told you, area, cross section area of this core material, and n square is the number of turns, n power 2 is the number of turns, maybe 100, 50, 10, whatever, and L is the length of these turns after it is rotated. It's not the length of the what we call wire or conductor. It is the length after the turns are rotated on a particular core material from starting to end. What is the length? Now mu is the permeability of the core, means how it is behaving, permeability. Okay, so now coming to the series and first equation, inductance is V is equal to L di by dt. So Total inductance series is nothing but L total is equal to L1 plus L2 plus L3. It's same like your resistance. If it is in parallel, 1 by L total is equal to 1 by L1 plus 1 by L2 plus L3, like this it will go. Now coming to the formula for energy, how the energy stored in the capacitor. E is equal to half CV square. The capacitance, the energy stored is given by half CV square. Just you have to remember this. We have some derivations for it. No need to go in deep. Just remember, energy stored in capacitance is given by half in capacitance multiplied by voltage square. Same inductance, it is half Li square, because always remember capacitance related with the voltage, that is voltage difference, and the inductance is related with the current, how much current it is flowing in that inductive material. So that's why it is half Li square, it is half CV square. Only we have to change. If you remember, capacitance related with the voltage means in equation it will come half CV square. If you know that inductor is related with the current, then you can remember half Li square, not the V square. So energy is equation is like half CV square and half Li square. And energy already you know, it may be joules, you can say. The unit is joules. Now coming to the some analysis here. We can see here what is node analysis, what is mesh analysis. So here by using the mesh analysis, the resultant current is given here. What are the voltages, what are the currents, you have to find here, and based upon the nodes you have to find here. Now coming to the mesh analysis, the first circuit is for the mesh analysis, second circuit is for the node analysis. For a single loop with a resistor and a voltage source, mesh analysis given as Vs is equal to IR1 minus IR2 equal to 0. If only we have two resistances and one voltage source, then mesh analysis is given as loop equation is given as V source minus IR1 minus IR2, where I is the current through that loop, which is won't change, it is same through the loop. So R1 and R2 are the two different distances. So it is a loop equation, we can say. So Vs is equal to IR1 minus IR2, which is equal to 0. Generally, for multiple loops, we can say summation of the V sources equal to summation of I into R loop, where IR is nothing but voltage drop. It's nothing but voltage drop summation is equal to voltage sources. So we can form the equation 1 here and equation 2 here. Then we can find the analysis by using elimination technique, or you can using the Cramer's rule, matrix Cramer's rule. Then you can find the what is I1 and I2, two equations, two unknowns, we can get the current. So as per the assumptions, the loop current I1 is nothing but your this I1. Okay, so whatever you got in the value of the I1 by solution, that is equal to I1, is got 1 ampere. Now as per the loop equation, this I2, which is nothing but I2. So the whatever you got the I2 value after the solving the equations, that is nothing but your I2. Now what is I3? It's nothing but I1 is, if you are considering in this direction, I2 in this opposite direction, then I3 is nothing but I1 minus I2, I1 minus I2. But already we know what is I1, I2 by loop equations solution. Then I1 minus 1, it will be 0. So it depends. It may be 0 or it may be vary. It depends upon the circuit values, resistance values, source voltages. Now coming to the node. Okay, before that, what is the steps we have to follow for mesh analysis? Mesh analysis steps are identify all meshes in the circuit. How many meshes are there means loops. Mesh here means loop we call. So in this circuit we have two loops, one loop and second loop. We have to identify first. Assign mesh currents to each mesh. Means I will assume this as a first I1 and this as a I2. Assign the mesh currents I1 and I2, and always use clockwise direction, so that easy for the calculation. Clockwise direction or anti-clockwise, anyone you can use, but use same principle to all the loops, all the meshes. Write KVL equation for each mesh. So if when the loop is coming to picture, which law will come? Kirchhoff's voltage law, KVL, which is voltage law, means sum of the voltages in a particular loop equal to 0. They may be a source voltage or maybe a voltage drops. So this is your equations where we have to write with a KVL format. Now solve the simultaneous equation to find the mesh current. So we have two mesh meshes here. So we have two mesh equations by using KVL. Then we can solve two unknowns and we can solve the values for the I1 and I2. Then we can find what is branch currents I1, I2 and I3. Okay, this is about the mesh. Now coming to the node analysis. For node analysis with multiple branches, let us take we have one and two branches, and one should be reference ground we have to take. Then it is nothing but V starting minus V minus Vn divided by R, which is equal to 0. V by R is nothing but your current. So it is called KCL, Kirchhoff's current law we are following here. So where Vn is the voltage at another node connected to the branch. So V minus Vn. So V minus Vn. So this minus Vn, another node is V2. So V, if we are considering V first node, then V minus V2 means V minus Vn. That's V2 here. And for this 2 ohm resistance, V minus 0. This is ground 0. Same here, V minus V2. We can say this one. Same if we rearrange for the node 2, this is the reference and this is the another node we call. So like this, V minus Vn divided by R equal to 0, all summation. To this node, how many are connected? First, you have to identify 1, 2 and 3 are connected. So for these 3, we have to write the equation, summation with the summation which is equal to 0. We'll see step by step. Identify all nodes in the circuit. So 1, 2, 3 nodes are there. 1, 2, 3 are there. And select a reference node or ground node. So all our many maximum nodes are connected to this point with maximum elements. So this is your reference node we are connecting. Sometimes the reference node is given also, or you can assume the maximum elements connected node or where the currents is leaving from that node we can see. So that will be accepted as a reference node or considered as a reference node. Now assign voltages to the other nodes. Assign voltages to the other nodes. That is first node it is V1, second node it is V2. Now write KCL equation for each node like this. You have to write the KCL equation for each node and sum it, except the reference node. So forget about the reference node. So we have two nodes with and one reference node. So we need Kirchhoff's current law to each node for all the branches of that node. So we have two equations now. KCL we are writing for these two nodes for all branches connected to that particular node. Now solve the simultaneous equation to find the node voltages. So we have to solve the simultaneous voltages to find the equation values. That is V1 and V2 are the unknown and V2 KCL equations we are getting. So like this we will get the values. So this is mesh and node analysis. Now coming to the, so let us consider this circuit, very big circuit we have. Now let us take, we want here in this resistance, the generally we call load resistance. If you want to vary, then how the current will change, how the voltage drop will be here, we have to check. So every time if you change the load resistance, if you put the loop analysis, mesh analysis, it become very big setup and it will take much time whenever we change the load resistance. So what we got it, we have some theorems where we just separate this complete one circuit and with a load resistance. So this complete A and B on the left side, what is the circuit, will solve it and will consider it like a fixed one, which is called maybe a Thevenin's circuit, or we can call it as a Norton circuit. So for that only we have to study what is the Thevenin's and Norton's. Now once this circuit is fixed one, then whatever the changes we are making in the resistance or load resistance value, then we can directly in one equation we can get the current and the voltages across this resistance. So that is, let's say this is the across A and B nodes we are connecting the load resistance here same. Now this is the voltage here. The current is coming from this equivalent circuit of this, let us take, that is called V Thevenin is the voltage and R Thevenin is the resistance of that big circuit in equivalence. So that's called, and same if you remove this load and you put RL, it will become like this, V Thevenin and R Thevenin in between two terminals, and this is your RL. Now, what is it? Steps we have to follow. So, identify the portion of the circuit means in between which nodes we want to find the equivalent circuit and equivalent voltage. We have to identify. That is between terminal A and B. We need a equivalent circuit, and between A and B on the right hand side we connect a load resistance which is always varying. We want the analysis every time. So choose the two terminals across which you want to find the Thevenin's equivalent. So we choose A and B on the left hand side. Then calculate the Thevenin's voltage. So how to calculate that one? So for that, remove this RL resistance, that is load resistance, if there is one. If it's not given, no problem. If it is there, remove it. And across the AB from seeing on the right to left, and calculate the open circuit voltage. What is the open circuit voltage here? We have to calculate. Like just here example, remove this RL here from this point, just see on the right hand to left side. So what happens? This is your effective circuit where 1 ohms connected terminal A and B, and this won't come into picture because this is open circuit now. Only this is your final circuit will be there where the currents will flow or voltages will be come into picture. We have to solve with the node analysis or mesh analysis or KCL, will apply it. Then you can get the final voltage across A and B. Then and final resistance. So this is only for voltage. What is Thevenin, which is nothing but VOC. Now this voltage that appears across open circuit at the terminals, that is nothing but Thevenin. This is Thevenin. Next we need Thevenin. How to find? Now, finding the Thevenin. Turn off all the independent voltage sources, replace them with a short circuit, and independent current sources, replace with them open circuit. Now, example this here. Remove this voltage source and short circuit this, and remove this current source and open circuit this, because current sources are open circuit and voltage sources are short circuit. So when this is short circuited, these two will become in parallel, 4 and 12, and 3 ohms will come into picture. When you open circuit this will become in series with the with this circuit. So these two parallel, it will be 3 plus 1, 4. 4 ohms will come as a open circuited Thevenin, because we have to remove this RL to always to think about the Thevenin and Thevenin. So Thevenin will be 4 ohms and Thevenin will be 30 volts, something which will come. So calculate the equivalent resistance seen from those terminals. By seeing from these terminals, calculate the equivalent resistance by removing the independent voltage sources as a short circuit and open circuit the independent current sources. So we will give a Thevenin is equal to R equivalent. So this resistance is equivalent resistance looking back, means looking from the right to left, back into the circuit from the open terminals. Now, what is Thevenin is nothing but VOC, open circuit. What is Thevenin is nothing but R equivalent, looking back into the circuit. Now the equation VL. So what is the VL? Voltage across the resistance is given by it's called voltage division rule. Thevenin divided by, so total what is the current here? Thevenin divided by Thevenin plus RL. Thevenin divided by Thevenin plus RL will give the complete current. So multiply with the RL is nothing but voltage across the resistance, we can say voltage across this resistance. So this is VL is equal to RL divided by Thevenin plus RL multiplied by Thevenin. Okay, so like this we have to find the load voltage. This is the load voltage. So if you want to change the load voltage for any 10 times, 15 times, 100 times, if you just change the value of the resistance here, substitute here RL, here, and we'll calculate the VL. No need to go for the big circuit analysis every time. So IL also is given by, what is the current here, IL in the resistance, because two resistances are connected in series. So Thevenin is the total voltage divided by total resistance. So you will get the IL. Okay, this is about the Thevenin. Now come to the Norton. So if you calculate, we got Thevenin as 4 ohms for the circuit, Thevenin as 30 volts, and RL if you consider as 6 ohms, then substitute in this, you will get IL is equal to Thevenin by Thevenin by RL, 30 by 4 plus 6, 3 amperes current is flowing in these two. And what is the VL? VL is given by I multiplied by Thevenin. So Thevenin is 30, I is 3. So 90 volts is the your voltage across the resistance. So like this we have to find. Okay. Next coming to the Nortons. Now let us say consider same circuit with a current source in parallel with a resistance. Then that is called Norton resistance, and this is called current source. We are making an equivalence with a current source in parallel with a resistance. We can find with the source transformation also from the Thevenin's equivalent circuit with current source with a parallel resistance. Okay, what are the steps? For example, this is the same circuit I am using here. This is the RL and this is your circuit where we have to make equivalence with a current source and a resistance in parallel. What is the steps? Identify the portion of the circuit, same like your Thevenin's. Choose the two terminals across which you want to find the Norton's equivalence. So these are the two terminals where we want to find the Norton's equivalence. Calculate the Norton's current. First, how to calculate the Norton's current? Remove the load resistance, if any. So we are removing this load resistance, if any. Now we have to calculate the Norton's current. So, okay. Calculate the short circuit current. Now, previously for finding the voltage across these two terminals in Thevenin's, we removed it, and open circuit voltage we find it. But current always flow in a closed path. So just short circuit by removing the load resistance. Short circuit here, and find the equivalent current in this short circuit wire or short circuit path. So calculate the short circuit current that flows through the terminals when they are short together. So when you short these two A and B terminals by removing resistance, then analyze the circuit and get the what is the current in this line, in this A and B terminal. Then that is nothing but I Norton's, which is called short circuit current. Now same, what is the resistance? Norton's resistance. Turn off all independent voltage sources, replace with the short circuits. Voltage sources remove and short circuit. And independent current source replace with open circuit. This independent voltage source replace with this one. Calculate the equivalent resistance seen from the terminals. Calculate the equivalent resistance seen from the terminals. That is from these terminals, open terminals. What is the equivalent resistance we have to check. Then this resistance is also called as looking back into the circuit is nothing but the resistance is equivalent resistance looking back into the circuit from the short circuited terminals. So the Rn equivalent to is nothing but same as your this one, what we call R Thevenin's. Both are same. Rn and R equivalent are both are same. So from this we can see In is nothing but short circuit current. Rn is nothing but equivalent resistance looking back into the circuit, means by opening the resistance looking back into the circuits. VL is equal to IN plus RL. That is, now we have to find what is the voltage across this load resistance. That is, what is the current IN multiplied by what is the RL. So once you know the IN, we can find IN into RL, which is VL. So another current through the load resistance. What is IL? IL is nothing but current division rule we can use. IN divided by total current multiplied by total resistance. That is Norton resistance divided by total resistance. That is IN by RN plus RL is nothing but your what is called voltage I by R. Now multiply with Rn, you will get the current division with this in the load resistance. Now by solving the equation, we have Rn 4 ohms, which is equal to R Thevenin's. Both are same because procedure is same. Now IN is nothing but by short circuiting this A and B terminal, we got 7.5 volts. Now if we have RL is equal to 6 ohms, then find what is the VL and IL. So IL is given by IN multiplied by RN. IN is nothing but 7.5. RN is 4. Now divided by RN plus RL. RL plus RN. So what is RL? 6. 6 plus 4, 10. So 4 into 7.5 divided by 10. So we'll get 3 amperes, same like the previous one. So like this we have to find the Norton's equivalence, Norton's current, and Norton's resistance, and load resistance, load current, load voltage. So by relationship between Norton and Thevenin's is nothing but V Thevenin's is equal to IN multiplied by RN. Also we can say R Thevenin's is always RN. So generally this V Thevenin is equal to IN multiplied by RN as per the Ohm's law also we can use. So this is also come with the source transformation technique. We can use, that is always this one resistance and one current source is equivalent with a voltage source with a series resistance, like that. Now coming to last two pages. Now a sinusoidal voltage or current can be expressed in terms of V of t, that is Vm sin omega t. Sinusoidal form always comes under alternating current. So sine is nothing but sine wave, like a sine wave, you know the sine wave. So alternating current will be with like this. V of t means instantaneous voltage is given as Vm sin omega t plus phi. Vm is the maximum voltage which is going from 0 to maximum or from maximum to 0. That is Vm. The maximum height it is approaching from 0 to. So there is a maximum voltage. And sine omega t is the shape of this curve, how the voltage is performing. 0 to maximum, maximum to 0. Again 0 to negative maximum and negative maximum to 0. This is called one cycle. Omega t is the angular frequency, omega t. 2 pi you can use here, 2 pi t. Or if you have in terms of frequency, 2 pi f we will use omega t. And is the phase angle. Plus phi is if we have voltage and starting from 0, then it is called 0. If it is starting other than 0, then how much it is delayed, how much it is advanced, then it is coming the angle. Now, where V of t is instantaneous voltage or current, maybe current is there, I of t we can use. Vm is a maximum voltage, peak value. Omega is the angular frequency in radians per second, which is given as 2 pi f we can use. And t is time. Phi is the phase angle. Phi f here is the frequency, how fast the waveform is moving. So phase in AC circuit indicates the timing relationship between voltage and current waveforms. Means voltage is started at 0 degrees and current is started at the same 0 degrees, then it is called in phase. Means generally it happens with the resistance. Now if the voltage started at 0 degrees and current starting at some delay means plus some 10 degrees, 20, 50 degrees plus, then the voltage is 0 degrees and current is starting with the delay means minus means delay. So current is nothing but with a minus 10 degrees, minus 20 degrees, then it is called lagging. So the current is lagging the voltage. Generally it will happens with inductance. Now when the angle is for the current is plus 10 degrees, plus 20 degrees, plus 30 degrees, then that means it is starting before the voltage. So it is called leading. So that leading is comes with the capacitance. Okay, so we'll see that one. Now capacitance is nothing but in terms of reactance and admittance and impedance. Then capacitance with the reference with the AC circuit is called reactance. Decreases with increase in frequency. That is Xc is equal to 1 by 2 pi Fc is the equation. That is capacitive reactance. Whenever frequency increases, the value of the reactance will decrease. The equation is 1 by 2 pi Fc. Consider to inductance, and it is XL is equal to 2 pi FL. It is a proportional. 2 pi FL, it is inversely proportional with this its value. So capacitors allow more current to pass at higher frequency. So capacitor allows more current to pass at higher frequency. So we need a higher currents for higher frequency. Inductors oppose current flow more at higher frequency. It opposes because it's a proportionality constant. So XL is equal to 2 pi FL. Now another, if you what is a full form of this is nothing but X is equal to 1 by omega C. Generally omega already we know it is 2 pi F. So 1 by 2 pi Fc, that is capacitive reactance. X is the capacitive reactance in ohms. It's similar to Ohm's law we can use. That is, but its equation is 1 by 2 pi Fc. F is the frequency in hertz, C is the capacitance in farads, and omega is the angular frequency to 2 pi F. Same effect of frequency. So as frequency increases, as frequency increases, Xc decreases. Inversely proportional, meaning that the capacitor allows more current to flow at higher frequency. Means what it means? Capacitor allows, means the capacitor allows more current to flow at higher frequencies. Higher frequencies, then capacitor allows more current. Capacitor pass AC signals better at higher frequency. Means AC signals communication for communication circuits is called AC signals. So where better outputs will get at higher frequency. If you increase the frequency, then it will allows the more current. So it is useful in the communication network capacitors. Now inductance, inductive reactance is nothing but X is equal to 2 pi FL. The reactance of an inductor increases with increase in frequency. It is given by the formula. XL is an inductive reactance in ohms and L is the inductance in henries. Effect of frequency on inductance. As frequency increases, XL also increases, meaning that the inductor opposes, means it stops. It opposes the flow of current more at higher frequency. It allows more current. It opposes the uh, current at higher frequency. Therefore, inductor blocks AC signals more effectively at higher frequency. The jammers always work with the inductance because we have to block the high frequency communication. Then we use inductance in the jammers. Last slide, we study what is capacitive reactance and their relation between voltage and current. So already we know this, and another Excel also we know this. Then what is the impedance? Means if inductance and capacitance both are connected, then what is the result? So result is nothing but always we have resistance also, because in the universe we don't have a pure capacitance or pure inductance. It have always with a resistance. So when there's a RLC circuits are there connected, R, L and C. L is inductance, C is a capacitance, R is a resistance. Then what is impedance? That together is called impedance. That is equal to under root of R square plus XL minus XC whole square. So Z is the impedance in ohms, R is a resistance, XL is inductive reactance, XC is a capacitive reactance. So if let us take a sinusoid form, we have voltage and currents like this: Vm cos omega t if cos sign is there, if Vm sin omega t if sin form is there, same if current sign there. Then this is the time domain where t time is coming omega t, then it is called time domain. Now we have to transform to phasor domain, because calculation or analysis, circuit analysis is easy in the phasor form, not in the sinusoid form, because sinusoid form consider with sine, cos term, integration, derivation is very difficult. So in phasor form, there is no sine and cos term. So directly we can calculate with a complex values, with a complex value. Vm, so Vm cos omega t plus phi is transformed to phasor domain as a Vm phi, where Vm is the magnitude and phi is the angle. Now Vm sin omega t, Vm, because reference always with the cos, so that's why Vm phi will be there. If the sine format is there, then we have sine and cosine always will be lagged with a 90 degrees. So cos to sine, cos is, let us consider as a 0, sine will come after the 90 degrees. After the 90 degrees, then sine term will start. So it is Vm minus 90 degrees. Same cos Im is Im theta, then sine is nothing but theta minus 90 degrees. Summary of voltage current relationship. If let us take R, L, C are the elements, then what is in time domain? It is nothing but V is equal to instantaneous voltage is equal to R into instantaneous current. V is equal to L di by dt. So here in time domain always we have a differentiation or integration sometimes. Okay, based upon this equation. So time domain we have to use differentiation effects. V is equal to L di by dt inductance. For capacitance, I is equal to C dV by dt. So means every time this cosine sine terms we have to integrate and we have to apply the rules. It's difficult. So if you go for the phasor domain, it will be easy. So how it will be phasor? So that is frequency domain we call. Phasor domain or frequency domain are same. So R is given as V is equal to IR, same Ohm's law. Same L we have V is equal to J omega Li, same like Ohm's law. So J omega L is your inductive reactance, R is your resistance, and here V is equal to I by J omega C. 1 by J omega C is nothing but your capacitive reactance. Same like Ohm's law we can apply here. So in frequency domain for AC circuit, Ohm's law will apply. We know that Ohm's law will apply for only DC circuit, V is equal to IR, but in AC circuit also will apply based upon its frequency domain, based on its frequency domain by these equation J omega L and 1 by j omega c equations. Example of this is there. And let us take Vs is nothing but 10 one capacitance resistance is connected. Vs is given as 10 at an angle 0 degrees, because consider 10 cos omega t, Vm cos omega t plus phi is not there. So Vm cos omega t, omega is here 4. So Vm cos 40, Vm is 10, 10 cos 40 is there. Its phasor domain is just Vm and it's an angle phi. So phi is not there. So 0. So what is Vm? 10 and angle is 0. So Vs we are considering. Now consider what is Z. Z is nothing but summation of these two. There is no inductance, only these two we have. So 5 plus what is phasor, that is what is it, capacitor. Yeah, capacitor time domain is this one. We need phasor domain, that is frequency domain. What is the capacitance in this one? That is 1 by j 2 pi fc xc, that is 1 by j 2 pi 2 omega c means 2 pi fc. So 1 by j 2 omega c. So apply phi is phi as it is, 1 by j omega. What is omega here? 4t. So j4 multiplied by what is c? 0.1. So 1 by j 0.4 will come. Then now solve this equation, we will get the equivalent impedance of this one. Once we get the equivalent impedance, like Ohm's law, Vs that is Vs divided by Z is nothing but your I. I is equal to Vs divided by Z. Apply here. Or V is equal to, if you want V at a capacitor, is nothing but what is the current multiplied this reactance Zc. So this is your voltage across the capacitor, 4.47 minus 63.43. So okay, so this is how all the slides are completed. Now we have some examples, MCQs. So like this, what you can solve uh, by observing these slides. So we'll stop here. Thank you.